All right, now we're moving into shear and moment diagrams for coplanar frames, meaning frames that are all in the same plane. We're not talking about 3D, basically 2D frames. Frame meaning we have beams and columns. So the procedure, right? If we want to develop shear moment diagrams for a frame, it's the same as a beam, except now we have vertical and horizontal members, right? So now we have horizontal and vertical members, and they're connected. How are they connected? We have two different types. We have a pin or hinge connection. Which is basically if we take our beam and our column, they're connected by a pin. It's analogous to a beam, two beams that are connected by a hinge, right? And if we remember back to the lecture on idealized structures, we know that pins or hinge connections can only transfer forces. So Fx and Fy and Fz if we were in 3D. So we could have a pinned connection. That would be like a braced frame, right? Where we have pin connections. Or we can have a moment connection or a fixed connection. And that would look like how we drew it earlier, right? It's like a little, let's draw an actual horizontal beam. It's like a little triangle. And that would basically be analogous to a continuous beam, right? So a fixed connection transfers both forces and moments. which in 2D is fx, fy, and your moment about z, right? Let's make sure to be clear. Fx and fy in 2D, fx, fy, and mz in 2D. If this was 3D, it would be fx, fy, fz for a pin, and fx, fy, fc, mx, my, mz. Depending on the, it could only be in one direction, the moment connection, but which it likely will be, but yeah. Okay, sorry, my pages got a little bit out of order. So if we're looking at the procedure for determining my, for drawing shear moment functions on a frame, go back to our very first thing, calculating our support reactions. Separate your frame into individual members because we're going to draw shear moments on each member. An individual member would be a beam, a column, a brace, if we're talking about a diagonal piece. Separate your frame into each of its members. And then you got to separate those into each member into a different section based off of if you have any load discontinuities. Where there's a change in a load or an additional support, like if there's a beam with a roller or a pin in the middle of it. Right, and separate your members into different sections, which we've already been doing while we've been building our shear and moment functions. Determine your shear and moment functions. For each beam and its sections, or each beam, each member. Right? And then we will plot them. So globally determine your reactions at your supports, then separate your frame into individual members and find the shear moment for each member. You may have to break it up into different sections based off of changes in loading or supports that lead to discontinuities. Determine your shear moment functions, and then you get to plot them. So we're going to do an example of what that looks like. But we're going to do it on a different, oopsies. We're going to do it in a different file because I want that's not what I wanted. Oh yeah, it is. Here it is. Because I wanted a vertical sheet because it is easier for this example. So here's our frame example. We've got a beam and a column, and we have a horizontal load on my column and a lateral load on my column and a gravity vertical load on my beam. And it's got a fixed connection, so it's a moment frame. First thing we do is solve for our reactions. So what reactions do I have? At A, I have a roller, so I have a vertical reaction at A. At C, I have a pin, so I have a horizontal reaction and a vertical reaction. You can assume directions and then the signs will tell you otherwise. And I'm assuming those loads occur at the center of the beam and the column. So first, let's do the sum of the forces in the horizontal direction because those are easy. Oops, I wrote y and x. Those need to be opposite. Oh my gosh. Okay, hold on. RCY and RCX. Okay. So let's see. If I do the sum of the forces in the x direction, I get negative RCX plus 5 kilonewtons, right? That's the only horizontal force is my horizontal load. So my horizontal reaction at C is 5 kilonewtons it's going to the left. So now I have two unknown vertical reactions. So I'm going to do moments about A. To find one of them. I don't know why I'm doing that. Let's see. So I take the moments about A. I have 5 kilonewtons acting at 5 meters. Because I said it was halfway, so 10 meters divided by 2 is 5 meters. And it's acting clockwise, so it's negative. I've got 10 kilonewtons. Acting at 5 meters clockwise, so it's also negative. And then in the positive direction, I have my, let's see, I have my RCY acting at 10 meters. And my RCX acting at 10 meters counterclockwise, so it's positive. Right. If I solve for my RCY, my vertical reaction at C, I get negative RCX times 10 meters plus 5 kilonewtons times 5 meters plus 10 kilonewtons times 5 meters all over 10 meters. And I know that this is 5 kilonewtons, right? So my answer is RCY, right? Take out your calculator. All right, negative 5 times 10 plus 5 times 5 plus 10 times 5. Ooh, negative 5 times 10 plus 5 times 5 plus 10 times 5 divided by 10, 2.5 kilonewtons. And it's acting up because that's what I assumed, and it came out positive. Right. This is 5 kilonewtons, and this is 2.5 kilonewtons. So now if I do the sum of the forces in the y direction, I have RAY acting up plus RCY acting up, and the only other vertical force is my 10 kilonewton applied load. So RAY is 10 kilonewtons minus RCY, which was 2.5. So my reaction at A in the vertical direction is 7.5 kilonewtons. So that was just to find my support reactions. Always good to practice that. My dog just gave a big sigh. Apparently she's very bored. You probably are too. So let's look at the individual members, right? Let's see, I have my support reaction, 5 kilonewtons, that, and 2.5 kilonewtons there. And then I have 7.5 down here. So, one thing that's good to look at is make sure that the entire beam is in equilibrium. The entire column is in equilibrium. So let's look at, if I do the sum of the forces in the x direction on the beam, I have an axial force -5 kilonewtons going to the left. So on the opposite side, I need 5 kilonewtons going to the right. So that beam is in axial compression. And then I have, if I do the sum of the forces in the y direction, I need to have a shear right at B. This would be the shear right at B. Of 10 minus 2.5, so 7.5 kilonewtons. Let's see. And then if I do the moment at B, because this is a moment frame, so I can have moment. I need to have moment. If I do the moment at B, right before B, in the beam, I've got I've got 10 kilonewtons acting at 5 meters clockwise, so it's -2.5 kilonewtons acting at 10 meters plus my moment at B. So my moment at B is basically 50 minus 25. So it's 25 kilonewton meters, and it's acting counterclockwise. So I look at my joint, and it needs to have equal and opposite reactions, right? So horizontally, it's got 5 kilonewtons. Vertically down, it has 7.5 kilonewtons. And then acting clockwise, 25 kilonewtons. Gosh, my ends are looking terrible. Kilonewtons. There you go. So now let's look at the column, which would be easy. I wonder if I can rotate it. Rotate page. I don't think I can. That'd be fun though, wouldn't it? Well, you can rotate your piece of paper. I'm just going to rotate my head. So let's see. If I take the sum of the forces in the x direction, I have 5 kilonewtons acting to the right, so I need 5 kilonewtons acting to the left at that right before the joint B. If I take the sum of the forces in the x direction, or in the y direction, I have 7.5 kilonewtons acting up, so I need 7.5 kilonewtons acting down. And then let's take the moment at B for the column, right? If I take the moments at B, I've got, I don't have to take into account that 7.5 kilonewtons because it has 0 moment arm. So I just have acting counterclockwise, so it's positive 5 kilonewtons, right? Yeah, 5 kilonewtons times 5 meters plus my moment at B so my moment at B is negative 25 kilonewton meters, and it's acting clockwise. So let's draw it acting clockwise. Oops, that needs kilonewton meters. Make sure it says 25 kilonewton meters for the beam too. So again, my equal and opposite at my joint, I need to have 7.5 kilonewtons acting up, 5 kilonewtons acting to the right, and acting counterclockwise, 25 kilonewton meters. So what do you notice about the joint? The joint's also in equilibrium. That's good. It better be. All right? I have the 7.5 kilonewtons of shear coming from the beam and the 7.5 kilonewtons of axial force from the column. 5 kilonewton axial force from the beam is 5 kilonewton shear from the column. And I've got a counterclockwise moment in the beam, so I have a clockwise moment in the column. So that's just to show you step 3. Separate, wait, what did I call the last page? Right, this was 1 solve for support reactions. Right, I said my procedure, solve for support reactions, calculate support reactions, whatever you want to say. Step 2, separate your frame into individual members. And here's a chance for you to check that everything, that your beam and your column are all in equilibrium and the joint is all in equilibrium, right? Right, and we know, let's see, a fixed connection transfers fx, fy, and your moment about z. I'm going to say, remember individual members and joints are in equilibrium. So it's a good check, if you do that and you realize that they're not, then this point to step back and go check it out. And you might also notice here, let's see, axial force in your column is equal to shear force in your beam. Your shear force in your column is equal to your axial force in your beam. And your moment, in your column is equal to negative, right? Opposite direction. Moment in beam, opposite direction. And this is all at the joint. Okay. At the joint, your joint transfers axial force in your column to shear force in your beam, shear force in your column to axial force in your beam, and the moment, it just makes it in the opposite direction. I guess that's technically at, well, maybe. Okay. All we've done so far is solve for our support reactions. Now let's actually develop our shear and moment diagrams. So I'm going to look at my right, this is basically 3 and 4. Steps 3 and 4. Members into sections and find V of X and M of X. And now we're actually finding axial load too. All right, now that we have columns, we do have axial load. Previously, we've been ignoring it. So I've got 2 sections. All right, one before and one after if I assume my X is going this way. You could also call it Y because it's vertical, if you want. So let's see. For 0 to 5 meters, right? That's where that happens. I have I have a roller. The only force is my vertical reaction. I'm just drawing it horizontally because it's easier. I guess technically maybe I should draw it vertical. Fine, right? I have what? 7.5 kilonewtons. And then I have, let's see, I have shear and moment and an axial load. So let's see. Sum of the forces in the x direction. All I have is my shear, so my shear is 0. There's no shear yet on my column. If I do the sum of the forces in the y direction, I have I have 7.5 kilonewtons plus my axial load is 0. So my axial load is a constant negative 7.5. And then if I do the sum of my moments at that section right there, I don't have any moments because that 7.5 kilonewtons is acting in line and there's no moment arm. So for the first section of my column, there's no moment, there's no shear, there's only a constant axial load. Now let's look at the second section of my column. I have, let's see, for 5 meters to 10 meters. I have this column here, and it has I'm gonna give myself room. It has reaction 7.5 kilonewtons. It has acting at 5 meters. It has 5 kilonewtons. Then it has shear and moment and axial load. Right? If my x is starting here and this distance is x minus 5 meters, because my 5 kilonewton force starts acting or is applied at x equals 5 meters. So let's see. Do some of the forces in the x direction. Well, now I do have one, right? I have my 5 kilonewtons and my shear. So my shear function is negative 5 kilonewtons. If I do the sum of the forces in the y direction, positive up, I have 7.5 kilonewtons plus my axial load is equal to 0. So I still have that constant compressive load of 7.5 kilonewtons. All right, I have a constant shear after I apply the horizontal load, and then I have a constant axial load. If I do the sum of the moments about where I cut my section, right, if I do some of the moments right about there, I get to ignore my 7.5 vertical reaction, but I have 5 kilonewtons acting counterclockwise, so it's positive 5 kilonewtons acting at x minus 5 meters. And then I have my moment. So my moment at x is equal to negative 5 kilonewtons, x minus 5 meters, right? So that makes sense because I said I'd have a negative 25, or x minus 10 minus 5. 5 times negative 5, 25 kilonewton meters. So that's the 2 shear, moment, and axial functions in my column. Now let's look at my beam. Again, I'm going to break it up into 2. Let me see. What did I had to draw them right. For completeness, let's put 7.5 kilonewtons right there. So I can do one of 2 ways, right? Well, let's first draw the reactions. I've got 5 kilonewtons acting horizontally and 2.5 kilonewtons acting vertically at C. Now, one thing I could do might blow your mind. I could just start my X here. So I'm going to do it. If not, I would have to also remember what was going on up there. Yeah. Actually, technically, let's see, I have 7.5 kilonewtons there. Sorry, I'm back at the column. I've got 5 kilonewtons and then 25 kilonewton meters. right? So that's back at the column. If I take the column as an entity by itself, I need to have all of the reaction, right? Now I'm going to look at the beam by itself, acting equal and opposite. It has the 5 kilonewtons, the 7.5 kilonewtons acting up, and counterclockwise 25 kilonewton meters. I'm going to break it up into 2 different sections because I've got this discontinuity of my concentrated load right there. So looking at from 0 to 5 meters, I've got my 5 kilonewton horizontal reaction and my 2.5 kilonewton vertical reaction. Now, if you remember our sign convention, go back and look at it. Downward shear is positive if I'm coming from right. If I'm coming this direction, that's my sign convention. If I'm coming from the other direction, I need to be equal and opposite. So up, clockwise, and go back and refresh that from earlier if you have forgotten that. So I have shear acting up, moment acting counterclockwise, and axial force acting to the left because its tension is positive, right? So let's do the sum of the forces in the x direction. I have my negative 5 kilonewtons minus my axial force is equal to 0. So my axial force is equal to negative 5 kilonewtons. That means my beam is in constant 5 kilonewton compression. Let's take the sum of the forces in the y direction. I've got 5 kilonewtons acting up and my shear acting up. So my shear is constant negative 2.5 kilonewtons. Take the sum of the moments where I cut my section right here. Counterclockwise positive. So I have my negative moment because I assume, yeah, it's fine. And I have I get to ignore that 5 kilonewtons because there's no moment arm. all I have is the 2 kilonewtons acting counterclockwise at a distance x, right? So plus 2.5 kilonewtons acting at 5, or not 5 meters, with a moment arm of x. So my moment function is 2.5 kilonewtons times x. Now I'm going to look at my second section from my concentrated load to the joint, right? Here I have my pin, my beam. It's got, what do we have? It's got 5 kilonewtons acting horizontally, 2.5 kilonewtons acting vertically, and then it's got this 10 kilonewton concentrated force. If I assume that x starts here, then the distance from here to here is x minus 5 meters. Again, I get to draw my shear up this time. My moment clockwise, and my axial tension. Let's take the sum of the forces in the x direction. I've got negative 5 kilonewtons minus my axial function is 0, so I get to keep my negative 5 kilonewton constant compression force. Generally, axial force does not change over the length of a beam or a column, unless you have a cross-section change. Actually, that doesn't, no, that would be changing the stress. Or if you have, the only reason would be if you have another applied load, right? Then I take the sum of the forces in the y direction, acting up is positive. I've got my 2.5 kilonewton reaction acting up, my applied load of 10 kilonewtons acting down, and my shear force, or shear function, acting up. So I get to solve for that. V of x is negative 10 plus 2.5, so negative 7.5. Wait, hold up. Not negative, right? Equals 10 kilonewtons minus 2.5 is positive, right? Oops. So if I take the sum of the moments about where I cut my section, I've got my moment at x acting counterclockwise. I've got 10 kilonewtons acting at x minus 5, and it's counterclockwise, so it's negative. But I've got my 2.5 kilonewtons acting counterclockwise, so it's positive at a distance of x. I get to ignore that 5 kilonewtons. Right? So let's see. My moment at x is equal to 2.5 kilonewtons times x minus 10 kilonewtons x minus 5 meters. That results to did I not? Let me check a second. Yeah, okay. Is negative 2.5 kilonewtons. Sorry. Negative 7.5 kilonewtons times x plus 50 kilonewton meters. So at x equal to 10, I have negative 25. That's wrong. I have a sign wrong somewhere. No, it's negative. What did I have drawn earlier? Let's go up. Okay. Huh? Yeah. Okay, sorry. Being weird. So why do I have positive shear but negative? Anyway, okay. So those are my functions for my beam. Oh, I guess that makes sense. What happens is at the joint, right? If I'm looking coming from the joint is 25 kilonewton meters, so my immediate response would be a negative 25. Okay. Yep, that's right. Okay. So those are my shear and moment and axial functions. So let's do what they look like. If I draw, let's see, if I draw my shear diagram, I'm going to copy this actually. Oh, I can't. Wouldn't that be fun? Right. If I draw my shear diagram, it would look like, right? Let's see, for my column, my shear is 0 for the first 5 meters and then a constant negative 5. Right. So it is 0 and then if that's the middle, 0 and then negative 5. Right? If I have my beam has, coming from the right, negative 2.5 and then positive 7.5 after we apply a 10 kilonewton load. Right, negative 2.5 and then positive 7.5. Right. Remember, notice the difference here is your 5 kilonewton applied load. The difference here is your 10 kilonewton applied concentrated force. If I do a moment diagram, I've got, let's see, for my column, I have 0 moment for the first 5 meters, and then afterwards, negative 5 kilonewton minus 25 meters. So at 5 meters it's 0, and then it increases linearly to negative 25. Right? It's 0 and then minus 25 kilonewton meters. It's a linear relationship. For my beam, let's see. what would be my value at 5 meters? All right, let's check. Where I have my concentrated force, so, and I cross 0, so I'm gonna have some kind of maximum there, right? Is 2.5 times 5, which is 12.5, I believe. Yep. Let's make sure down here it does too, right? Moment at x equals 5 meters is negative 7.5 times 5 plus 50. And my moment at x equals 10 meters is negative 25. What am I saying? Kilonewton meters. Kilonewton meters. So I've got a value of negative 25, and it goes up to 12.5 in the middle. Where's the middle? Right about there. So, and it goes down to 0 because it's a pin. Negative 25 kilonewton meters. Positive 12.5 kilonewton meters. Right? So what do you notice? That continuity, right? I don't have continuity for my shear because shear is axial and then axial is shear for the beam and the column. But I do have continuity for my moment. If this were presented on a on structural analysis software, you don't have to draw this if you don't want. If this was presented on a structural analysis software and the two were actually connected, it would show like that and so it would show like that for the beam, and let's make the column green. It would show like that for the column, and you would see that these two values, these would be, oops, these two values would be the same. So that is how you do shear and moment diagrams on axial in your column is shear in your beam, and vice versa. Right? So that is how you do shear and moment diagrams for a frame. Functions, again, make sure that you have equilibrium in the individual members. And you can check that, making sure that the joint is also in equilibrium. And you should have continuity. For a moment function, you should have continuity in your moment that's being transferred. It's harder to tell that by the shear and axial force diagrams because those are axial is because axial and shear are interchanged, right? Thank you.